Hey students, welcome to class 6. So we talked in the last class about how we need to clamp the part against the locators using clamps. But we didn't really talk about how to calculate the forces that are needed. So that's what we're going to talk about in this class. So let's get right after it. There we go. The amount of force that it requires matters a lot to the process that is going on. So in the upper left-hand corner here, you can see an inspection fixture. So it has locators, just like any of the others do, but the clamping is just little flimsy spring clamps. And so in the CMM labs, you may have used this type of spring clamp. They hold things in place, but they wouldn't hold it against any sideways force at all. It's only keeping it so that if you happen to bump the table, the part doesn't shift around, and that's all those do. On the other hand, welding and assembly over here on the right side needs some more level of clamping. Sometimes we need to be able to hold a piece flat or deflect a piece a little bit to get into the shape that we need so that we can put it together, especially with sheet metal where it may be a little bit warped or out of shape. We also need to figure out how to resist the shrinkage forces that are happening in a welding process, and sometimes we want to really reduce those or completely resist the shrinkage, and sometimes all we want to do is just accommodate that shrinkage without causing more warping to happen. But that's sort of a mid-level of clamping, and you can see that this uses toggle clamps, and if you remember from our last set of videos that we were watching, toggle clamps are good for sort of medium forces. They're made of sheet metal, they're not really strong, but they do a good job of holding things in place, kind of a medium amount. And then down here at the bottom you can see this fixture, which is for machining. It has big burly clamps. These are all hydraulically actuated, and you can see how these would swing into place and clamp down. That's kind of a nice feature of these. It looks like this is going to clamp way out here at the side and the locator's there, but in fact these rotate and then clamp, and that allows them to move out of the way when the person or the robot loads this fixture, and then they swing into place and clamp down. And when they do that, that keeps the part there, keeps it from deflecting. Another advantage of this particular fixture is you can see it's on a rotary trunnion here, and so it provides a fourth axis of motion to the machine tool so that the machine can access more areas of the part without having to refixture. Notice also that this one has a setup that is off at an angle, and so with a fixture that is dedicated like this one, you can do something like that, where if you have some features that are off at an angle, you can have a fixture that is tilted, and that way you can make them on a 3-axis machine tool, which is less expensive than going and getting a 5-axis machine tool. So in all of these, when we are figuring out what to do, we must consider the process load that's going to happen. We must consider what part deflection might happen, and also deformation that we might cause by indenting the part or by clamping it too hard. And so those are 3 things that we need to consider. We want to clamp hard enough that the part will not move. We want to not clamp so hard or clamp in the wrong place so that we deform the part, and we don't want to leave large indentations in the part. Sometimes small indentations are okay, and sometimes they aren't. It just depends on the part that you're making and what is needed. Okay, so in thinking about this, it depends some on the kind of clamp that you're using as well. Some clamps, like many toggle clamps, just apply one force. You pull the handle till it clicks and it applies one amount of force. And if the machining process comes in here and deflects the part a little bit, such that this interface between the tool and the clamp moves even the smallest amount, then this tool won't be applying the same force. It will be applying a smaller force. In addition, some of these are spring-loaded, and so you cock this back and it applies a good amount of force, but it has a little bit of spring compliance in it. That's really nice because it allows this to accommodate different sizes of parts. However, those different sizes of parts will be held with slightly different loads, because as you compress that spring more or don't compress it as much, the amount of force will change. On the other hand, if this is a hydraulic clamp rather than hand-operated clamp, then it will have pressure applied to it, and it will apply the same amount of force to the part no matter what the position is, because it's based on the pressure that's being applied. When we think about this, we can think about applying a force, and if we apply it in the same direction as the toggle clamp, then our locator over here, if we're applying 500 pounds with the clamp and 400 pounds with the machining operation, this locator over here is experiencing 900-pound load. And so when we do our calculation, we have to sum those two together to think about whether this locator is going to indent the part or not. If it were going the other direction, and so the force were happening against the clamp, which of course is not our ideal direction for machining, but it often happens that for a little while we will be going against the clamps, just because we tend to now machine all the way around a part rather than just a simple machining process. That could mean, if we're applying a force of 500 pounds and our machining force is in the opposite direction at 400 pounds, it could mean that the force against this locator dips as low as 100 pounds. So that might be okay, that might not be okay. It just depends on what we're requiring. Remember, if we're depending on friction down here, we have the static coefficient of friction times the normal load. 100 times the coefficient of friction is a lot less than 500 or 900 times the coefficient of friction. And so we would be losing our friction force, which it could be what's holding this part from sliding into and out of the page or sliding up vertically out of the nest. So we have to be careful. If we were doing something in the hydraulic direction where we applied 400 pounds and 500 pounds, because it's independent of the position, we would still probably be at 100 pounds if they were going in opposite directions. If they're going in the same direction, then we would have 900 pounds on the locator. I guess one point of this is that if it were a spring and we reduce and the machining force deflects the part at all, there would be less deflection on the spring, so it would no longer apply its 500 pounds potentially. Okay, so our goals in clamping, there we go. Our goal in clamping is to create a force vector through every locator. Now we can create that force vector either directly by clamping across it, or we can create it through friction, or we can create it by imparting a moment. So we need to consider things like what size should the clamp be compared to the locator if we compare the sizes of them. Well, when we do this, what we'll find is that we need to size the clamps and the locators based on the loads that they will endure, and whether those the size and shape of the end of the locator will deform the part or not, whether it will cause contact stress on the part. We have to think about things like, should the clamp match some particular shape in the part? Should it have the same rigidity? Should it be less or more? And should the material be the same material, or should it be a softer material? And you can make different arguments depending on which of the different applications you're doing. A lot of times the clamp, the thing that actually interfaces with the material, is good if that clamping material is softer, because we're going to apply the force anyway, and we would like it to damage the clamp rather than damage every one of our parts that comes off. Sometimes it's great to mimic the shape so that the end of the clamp has some inverse of the shape of the part so it can sort of hold it better and support it better as it pushes into the part. But you have to be absolutely certain that in mimicking that shape, there is not a way that you're going to apply a moment that's going to pull the part off of the locators. And so that has to be done very, very carefully. What might prevent a clamp from being opposite a locator? That's a good question. And of course, that could be any number of things. It could be that a tool has to get to that location. And so we have to move the clamp away from the locator a little bit. It could be just that there isn't sufficient material on the other side. It could be that the other side that's opposite the locator is a super nice precision surface that we just can't clamp on. And so we have to go find a different location to achieve our clamping force. What would we do if the surface opposite a locator was angled? Well, that's a really interesting question, because then if we apply a force to an angled surface, not only do we get the normal force that we're wanting, but we get a component that is along that direction. So my applying the force this way also tries to push the part down and out of the way. And so when we do that, here we go, here's the part, and if I push on this edge, I will be imparting some force that moves the part down as well. In that case, we may have to think that putting the clamp on this side may not be the best. Now, if we already have locators that are preventing motion in that secondary direction, and we clamp against those locators first so that we know that we can't impart a rotation or a translation that we aren't intending, then we can go in and clamp against an angled edge. But if we're not sure that we can do that, sometimes we have to choose a different opportunity. We have to go clamp somewhere else on the part. What would we need to do if the clamp would be in the way of the process? Gauging, inspection, machining. Generally, we just move it to a different place. And then we have to make sure that we're not going to deform the part, that we're not going to warp the part, and make sure that we're not introducing a large moment that's going to spin the part out of the fixture. This question is, because clamps move, they tend to have more compliance than the locator. Is that okay? The answer is absolutely yes. The locators should not move. That's their point, is to locate. The clamps should have a little bit of motion in them, a little bit of compliance, so that if there is an irregularity or a tolerance issue with the part, the clamp still comes in and pushes on it and doesn't introduce an unwanted clamping direction or clamping motion. And so it is great if clamps have extra compliance. Okay, so that's what we're going to do right now. Next, we'll talk about what is the magnitude of forces, and then we'll talk about how to find those forces. All right, thanks for watching.